Good day, this is Dr. Wortel with a discussion on section 6.2, how to evaluate triple integrals. So just like in 2 dimensions, we're going to start with the simplest case where E is a rectangular box. And for that we have theorem 168, which states that, well, let E be a rectangular box, so x is between A and B, y is between C and D, and z is between P and Q. Suppose I have a continuous function f on E, then I can compute the triple integral as follows. We can compute it as a so-called iterated integral, just like in 2 dimensions. And what does this mean? Well, this means we have our inner function f, which we then integrate with respect to z, and we then treat x and y as constants. So a difference with the 2-dimensional case is now that we treat both x and y as constants, and we integrate with respect to z. So the dz here, the z, it goes from P to Q over here. After we compute that integral, we're left with this integrated function, which is now a function of x and y, because z has been integrated out. And that will have to be integrated with respect to y, and y goes between C and D. So y goes between C and D. Of course, we treat x as a constant in that second integral, and then y has been integrated out, and what's left is an integral for x, and x is between A and B. So it's the same procedure as in the 2-dimensional case, except we have a triple iterated integral. So as I said, these things are called iterated integrals, and just like in the 2D situation, we can also change the order. In the 2D situations, there are 2 different orders that we can use. But now, because we have 3 variables, you can actually see that there are 6 different ways in which you can order those. So there are actually 6 different ways in which we can compute an integral like this. Okay, so let me explain this by the hand of an example. Namely, I will do example 170 in the book. So in this example, we have to compute the triple integral over E of x over y plus z dv, where E is this rectangular box, where x is between 1 and 2, y is between 1 and 3, and z is between 0 and 1. So the first thing we want to do is invoke this theorem. So by this theorem, I can represent this integral as an iterated integral. And in this case, I've chosen to do it dx dy dz instead of the dz dy dx over here. You could also do dz dy dx. And as I just discussed, there are 6 different ways of doing this. But in this case, I will do it dx dy dz. And maybe you can try a different way yourself and see if you reach the same answer. So let's go and compute this integral. So what we do again is we compute the inner integral. So let me draw some imaginary brackets. So you don't have to draw these brackets, but just showing you that I'm going to compute the inner integral first, where I'm integrating with respect to x, it's dx, and I treat y and z as constants. So what I do is I leave the other 2 integrals there, because they will still be there, and now I will compute this inner integral. So I have to integrate x with respect x over a constant, because y and z are constants. So x over a constant, and the integral of x is x squared over 2. So what I will get is x squared over 2 times the same constant that I had before, namely y plus z. And this is between the boundaries where x is equal to 2 and x is equal to 1. And I still have my dy dz. Okay. So let's see what happens. If I plug 2 in, I get 4 over 2. And if I plug in 1, I get 1 over 2. And I have to subtract those 2, because it's that one plugged in minus that one. So I will get a factor 3 over 2, and I will take that factor out of the integral. So I'm doing like 2 steps at once. So if you don't follow me, please pause the video and see if you get the same thing as what I did. Okay, so now again we have to do the inner integral, which is an integral with respect to y, so we treat z as a constant. And we know the integral of 1 over y is equal to log y, and the z does not make a difference because it's just adding a constant. So you could do this with substitution, but you can also do it directly. So what we get is the log of the absolute value of y plus z. I forgot my outer integral, so I still have 3 over 2 times the integral from 0 to 1. Then I've got the log of the absolute value of y plus z, and that will be, that I have to plug in the bounds 3 and 1, and then I still have my dz. Okay, let's continue. So let's plug in these two values. So I get the log of the absolute value of, remember these are values for y, so we get 3 plus z minus the log of the absolute value of 1 plus z dz. Okay, at this point it's slightly convenient to note that we have 3 plus z, and z is between 0 and 1, and 1 plus z, and z is between 0 and 1. So all these things are positive, so we may as well not use absolute value, but just use brackets, because it's all positive anyway. Okay, what now? Okay, I'd like to integrate log of 3 plus z, and so now what I will use is the following thing that you've learned in first year, that the antiderivative of log x is equal to x log x minus x. So this formula can be easily checked by just differentiating this term. And if you remember how we obtained this formula, is we used integration by parts by multiplying log x by 1 and then using integration by parts. So that is how you actually obtain the formula. But checking isn't always easy because you just differentiate this. Okay, so what we get is, for the first term we get 3 plus z times log 3 plus z minus 3 plus z, and then we have to subtract 1 plus z times log 1 plus z, and then we have two minuses, so we get a plus, so we get plus 1 plus z. Okay, so I have integrated already, so I should not have written my integral sign. So this should be 3 over 2 times this whole expression, and this should be evaluated between 1 and 0. And then I end, so I have the big square brackets just to denote the multiplication by this factor 3 over 2 times everything. Because that 3 over 2 was in front of the integral, so that has to be multiplied by everything. Okay, so now I should plug in the 1, which will give me 3 over 2 times 4 log 4 minus 4 minus 2 log 2 plus 2. So this is plugging in 1. And then I have to subtract plugging in 0. And if I plug in 0, I get 3 for z. I get 3 log 3 minus 3 minus 1 log 1 plus 1. Okay, so let's think for a second. We've got a minus 4, we've got a plus 2, we've got a plus 3 because it's minus minus 3, and we've got a minus 1. So minus 4 minus 1 plus 2 plus 3, so all of that cancels. 1 log 1 is just equal to 0, because log 1 is equal to 0. So the final answer is 3 over 2 times 4 log 4 minus 2 log 2 minus 3 log 3. Okay, so that is fairly straightforward. Now the question is, how do we deal with the more difficult integrals? Excuse me, I mean, how do we deal with the more difficult regions? And this is what I'll explain now. So as an example, here we have a picture from remark 73, and this is the kind of regions we're going to look at now. So here we see that the region E is given by this thing over here, between these two surfaces, given by this formula z is u1 and z is u2. So how can we describe our region E? Well, we can see that, well, we can look at the shadow of the region E on the xy plane, so that's the projection on the xy plane, that's a region D. So we see that our region E precisely consists of those vectors x, y, z, such that xy is in this region D over here. And furthermore, the z-coordinate is precisely between these two surfaces. So that's a description of our region E, and we will call this a type 1 description. So, our region E is those points x, y, z, which as I just said. xy is in some region D, which is a region in the xy plane, and z is between two surfaces u1 and u2. So this is what's called a type 1 region. And if we have a type 1 region, then we are going to compute the integral as follows. So now the question is, how do we compute the corresponding integral? And the answer is, okay, we have a double integral over D. And then we have a single integral from u1 to u2 of f, x, y, z, dz. And then we have the dA. So, how do we think about this? Again, we can draw some imaginary brackets here. So we first compute this inner integral, where we integrate with respect to z, keeping x and y are constants. And then afterwards we plug in these two boundaries, so this time in terms of x and y. So after all that's done, the inner integral is going to be a function of x and y. And this function will have to be integrated with respect to the region D, and it's going to be a double integral. To compute such a double integral, we can use all of the techniques that we've learned in chapter 5. So for instance, you see that in this case, our region D is a rectangle. So then we can just compute this as an iterated integral. However, in general, the region D need not be a rectangle. So it's more like a happy coincidence that in this case, region D is a rectangle. But if it's something else, we can just use the techniques from chapter 5. So for example, we could again make region D like a type 1 or a type 2 region in the plane. So we could make this double integral also an iterated integral. And this is how we most often will solve such questions. So this is a type 1 example. I will give an example in a minute, but let me first continue with type 3, because there are other types. There's also type 2 and type 3. So I will not do type 2, but type 2 is going to be very similar to type 1 and 3, so you can think about that yourself. So what's going on in type 3? So here we have a region from example 176. By the way, I will not do this example, so after this video I recommend that you take a look at this example yourself. Just want to have a look at the region here. We can see here that the region can be described as follows, that the xz, they are all in this red circle, so this region D. Then the y-coordinate is going to be between this curve over here. So it's a surface, three-dimensional surface, and this is also a three-dimensional surface, this circle over here. So y is going to be between this surface over here and this surface over here. So E can be described as those x, y, z's, such that xz is in D. D is now a region in the xz plane. And the y-coordinate is between my two surfaces W1 and W2. Yeah, so this is how you could describe a region as a type 3 region. In this case, you can show that the triple integral over such a region is going to be equal to, again, we're going to have a double integral over D, and then the inner part is going to be an integral from W1 xz to W2 xz f x y z dy, and again dA. So again, how to compute this? We again write imaginary brackets. We compute the inner integral which we integrate with respect to y, and what's left is going to be a function of x and z. And then we do this double integral, but now in the xz plane. And it's going to be the same as the xy plane, right? X and z are just names. So it's going to be a double integral like we are used to. In this case, we see, for instance, that it's an integral over a circle. So maybe we could use polar coordinates, or we could also split it up like the circle. But you can read in the book on example 176 how they do this. I will finish this video now by doing two examples. So in the first example, we're going to do example 174 in the book, but with a little twist. So in this example we have to compute the triple integral over e of the function 2x minus y dv. E is the region in the first octant, so that means x, y and z are all three bigger or equal than 0, so that's the analog of the first quadrant in 2 dimensions. But below the plane x plus y plus 2z equals 2. Remember, this is the linear equation of a plane. As we know, the only way that we can deal with such a question is to first sketch it, right? Because otherwise we have no idea what we have to do. So let's start sketching. So what we want to do is we want to sketch this plane over here. And so the easiest way, we know it's a plane, so if we can just find the points on all the axes, we know how it looks like. So for instance, if x and y are 0, then 2z equals 2, so z is equal to 1. So, this point 0, 0, 1 is going to be on the plane. And similarly, if x and z are 0, then y is 2, and if y and z are 0, then x is 2. So we get this point and this point. And so we see that the plane, we have this triangle. So this is the point where y is 2, and this is the point where x is 2. And the plane just extends linearly from this triangle. Okay, well, we know that E is in the first octant, so E is over here. So it's going to be exactly the thing below this triangle over here. That's going to be our region E. So E is that region bounded by all the coordinate planes and this triangle, basically. So now we have to decide whether to do it as a type 1, 2 or 3 region. And the book does this as type 2, but in this example I'm going to do type 1. So you can see the contrast between the two. And so afterwards I would recommend that you look at the book and see how you can also do it as type 2. So if you want to do it as type 1, then that means our region E is going to be the x, y, z, such that x, y are in some region D, and z is between two functions. Okay, for the moment, let's for the moment call them u1 and u2. And remember that D is going to be the shadow on the xy plane. So in our case, let's do it in red. We can see that we have to integrate over this part over here, right? That's our region D. Okay, so we know our region D. Next thing we need to know is we need to know the bounds for z. So z is above some kind of surface and below some kind of surface. You can see in the picture that z is going to be, the bottom surface for z is just exactly the same as the region D, and this is where z equals 0. Right? So this thing is just equal to 0. Question now, what is the top surface? Well, you can see from the picture the top surface is exactly the triangle. And in triangle we have this equation. So we want to rewrite this equation as z equals something. So let's take this equation over here and let's compute a bit. So we have x plus y plus 2z equals 2. So 2z equals 2 minus x minus y. So z equals 1 minus x over 2 minus y over 2. Right? This is the formula for this top plane, but now written in terms of z, because z is between the bottom plane, which is 0, and the top plane, which is 1 minus x over 2 minus y over 2. So this thing here is 1 minus x over 2 minus y over 2. Okay. So now what we could use is we could use the theorem that I previously explained. I did not give it a number, so we can say that the triple integral over this region E of my function 2x minus y dv is equal to the double integral over D. And then we have the integral from u1, which is equal to 0, to u2, which is 1 minus x over 2 minus y over 2. And then we get 2x minus y dz dA. So it is actually convenient at this moment to also split up the region D as a double integral. I could do this first, but it's actually more convenient to just split everything up fully and then in the end only start the computation. So instead I'm going to look at the region D. So the region D is like this. Let's draw the region D again. But now in the xy plane, right? Our region D is in the xy plane. So x, y, and we can see that it looks like this. Right? D is this triangular region over here. So if we want to transform this as an iterated integral, we could again use type 1 or type 2. Well, let's just use type 1. I find it usually easiest. Because in type 1 we say, well, x is between 0 and 1. And so x is between 0 and 1. And what about y? Well, that's between this bottom curve, which is 0, and the top curve, which is, if you think about this is 2 minus x. Okay, so we've got those things together with let's do together with this. Let me write this over here as well. So z is between 0 and 1 minus x over 2 minus y over 2. So now it's convenient because we've got bounds for x, for y, and for z. So actually, the point that I'm trying to make is that this integral that I wrote over here, this is what we use in the theorem. However, this is actually not necessary, so this is why I'm putting it between brackets. I might as well just go do this computation immediately, so skip this step, and just find the bounds for, I found the bounds for z first, then I can find the bounds for x and y, which are over here. Then I've got the bounds for x, y, and z, and now I can immediately write the integral. So I have to do z first, that's by first I mean that's the inner part. So we have the integral from 0 to 1 minus x over 2 minus y over 2, 2x minus y dz. And then we're going to do the dA as in type 1, so that's going to be dx dy. So that means that, it's type 1, which is dy dx. dy dx. So y is between 0 and 2 minus x. And x is between 0 and, this should have been 2. It was between 0 and 2. Yeah, this is 2, this is not 1. So in this way, the point is here that if I start here and I just compute the bounds for z first, and afterwards I also start computing the bounds for my region D, like this, and I've got all these three bounds, I might as well write down this step immediately. So this step is not actually strictly necessary to write it down. You can go from here directly to there. Okay, let's start computing this a little bit. So we have the integral from 0 to 2, the integral from 0 to 2 minus x. Then we have to integrate this with respect to z. And remember, we have to treat x and y as a constant. So what you get is, well, that's easy. It's just 2x minus y times z. Between the boundaries 0, 1 minus x over 2 minus y over 2. dy dx. Okay, next step is just plugging in these two bounds. But you see already this is a polynomial. 2x minus y is a polynomial. So what I will get is just some big polynomial. Well, I've worked out here the equations myself, but it's just a lot of computation. But nothing is difficult, right? We know how to do this. We've done this a lot already in chapter 5. So you can check yourself. It's a good exercise, but it's not difficult. It's just tedious. But after a lot of computation, you see you will get an answer 1/3. So if you feel you need some more exercise with this, please check that yourself that you get 1/3. But it's a little bit of a tedious computation. Also know that it's exactly the same as the answer from the book. Before I continue with the last example, let me first explain one more concept. So remember, in 2 dimensions, we could define the area of a region D as the double integral over D of the constant 1 function. Exactly the same principle applies in 3 dimensions, so we can define the volume of V as the triple integral over E of the constant 1 function. So this is another way of computing volumes. In chapter 5 we've also seen other ways of computing volumes. We're going to apply this in example 177, where we have a region E described with some equations, and we want to calculate the volume of E. So first you want to sketch the region, and in this exercise this is already given, so the region looks like this. So we want to compute the volume, which is just some integral, right? So we want to think about whether this is type 1, 2, and 3. It seems to make sense to make it as type 3, because y is bounded between 0 here and 2. So let's do that. Let's say y is between 0 and 2. Now we can see that the region D that we have to integrate over is this region over here, which in the XZ plane I've drawn over here as well. But now there's a problem, because if you want to represent this region D as a type 1 or a 2 region in the XZ plane, we see that we run into trouble, because, well, if we do it as type 1, then we have to go from the bottom curve to the top curve. The bottom curve is a nice smooth curve, but the top curve is not a nice single curve. So we'd have to split it up again into 2 regions, which is annoying. If we want to do it as type 2, then we have to go from the left one to the right one. So this will be the start one, this is the end one. We see both of those curves have different behavior. So again, this leads to annoying things. So this is why the book says it is helpful to split E into 2 parts, precisely because of this problem which I discussed over here, that the region D over here is not easily described as a type 1 or 2 region. So let's take the part above the xy plane and the part below the xy plane. I've also drawn the corresponding region D for this part, and you can see this can be done quite nicely as a type 2 in the zx plane, and this can be done easily as a type 1. Anyway, let's write all of this down. So this is region E1. So let's do E1 first. Now let's do it in black. So E1, well, we've seen already that y is between 0 and 2. So let's write E1 in set notation here. So E1 is those sets x, y, z, such that well, y is between 0 and 2. And xz is in this region D1. So that's the red region, D1, which is also described over there. So let's go a little bit further, because as I explained in the previous example, I now also want to find bounds for x and z. This will make the computation slightly easier later. So the region D1 over here should be done as a type 2 region, right? So z should be between 0 and 1. So z between 0 and 1. And x is then between this curve over here and that curve over here. So this curve, this is where x is equal to z minus 1. And this curve, this is where x is equal to 1 minus z. So now I've gotten all the variables in bounds. Let me just quickly see if it's the same as my notes. Yeah. So that's the region E1. Let's do the same thing for E2. So that's those x, y, and z's. Again, where y is between 0 and 2. Right? We can see that in the picture. Y is between 0 and 2. And x is xz is in the region D2. But again, I would like to write it in such a way that I've got bounds for all the variables. So y is between 0 and 2. Now we have this region over here, and this can be nicely described as a type 1 region in the xz plane. Right? X is between minus 1 and 1. and z is between the bottom curve, which is x squared minus 1, and the top curve, which is 0. I'm struggling a bit with space, so it's the top curve is 0 and the bottom curve is x squared minus 1. Apologies, it's a little bit small, but hopefully you can still read this. But the point is, I've described both of my regions in such a way that I've done all of my variables. And now we can start computing things. So I've rewritten my two sets E1 and E2, and let's start with the integral over E1. Remember, we're integrating the constant 1 function. Okay, so now if you write it like this in terms of the three variables, you can basically use any order of the variables as you want, except for one big restriction, which I will explain now. So I'm first going to integrate over the x variable. And let's say, then with respect to z, z goes from 0 to 1, and then y goes from 0 to 2. So why do I integrate with respect to x first? That's because bounds for x are in terms of z. And the final answer of this integral is will be a number. It will not contain any variables. So if I integrate this first and I plug in some bounds in terms of z, then later on I have to do my integration over z. Otherwise the z will stay in the end, and that doesn't make sense because the answer should be a number. So if you have some bounds which are in terms of other variables, in this case x, they should go first, or at least they can never go last, because then the final answer will be in terms of z. So they should go before I'm integrating over that other variable, which is z in this case. This is why I'm doing it in this order, so I could swap those two integrals, or those two I could integrate from y after there. But as soon I should integrate with respect to x before I integrate with respect to z. Anyway, let us compute this integral. So I keep the integral from 0 to 2 and from 0 to 1, and then I get x between the bounds 1 minus z and z minus 1, dz dy. The integral from 0 to 2, the integral from 0 to 1. This is going to be 1 minus z plus 1, so that's going to be 2 minus 2z. Well, that's easy to integrate with respect to z. That's going to be 2z minus z squared between the boundaries 1 and 0, which is I get 1, and if I plug in 0, I get 0, so I will just get 1, and this is, you can check yourself, this is 2. Okay, so that was the integral over E1. Let's now do the integral over E2. Again, when writing the integral, I must make sure that the one with variables is as far to the inside as possible. That's just the easiest. So let's just do it like that. So let's make the inner one from x squared minus 1 to 0, 1 dz. And then let's do x and y from 0 to 2. Okay, so I get, oh, what's going on? I get the integral from 0 to 2, the integral from minus 1 to 1. I get z between the boundaries 0 and x squared minus 1, dx dy. So this is the integral from 0 to 2, the integral from minus 1 to 1. And then I get minus x squared plus 1, so 1 minus x squared, dx dy. Well, that's easy to integrate. That will give me x minus x to the 3 over 3 between the bounds 1 and minus 1, dy. Okay, so if you plug in 1, I get 2/3, and for minus 1, yeah, I do not want to do this computation, so check yourself that you get 4 over 3. and that is equal to 8 over 3. So those are the two integrals. Remember now the final computation is the volume of E is equal to the volume of E1 plus the volume of E2, which is the triple integral of over E1 plus the triple integral over E2, which is 2 plus 8 over 3, which is 14 over 3.